For many months, more than 4 million people walked across this floor. It's never polished, seldom buffed, never treated in any way. And yet, after this punishment, it looks the same as the day it was installed. This floor marks the path to a new industrial adventure, opened up by the peaceful applications of atomic energy. It's a symbol of the growing trend to produce new, improved materials with nuclear energy. In this case, creating an atomic revolution in wood. Applications of radioactive isotopes are already commonplace in many diverse industrial applications, ranging from controlling the thickness of rubber or gauging sheet plastic to assure a proper thickness, to testing welds and metal, to assuring the proper liquid levels in cans. Control of atomic energy has given technology a tool with which to create new products and improve old ones, and in the doing is generating a quiet revolution. Now, the fusing of wood and plastic by irradiation into an amazing combination substance promises to bring great benefits to the manufacturers and the users of wood products. It's an exciting story of development from an AEC-supported research to commercialization. Our story of this new atoms and industry adventure began at the University of West Virginia in 1961. The steps for making wood plastics turned out to be quite simple. Wood pieces were placed in an airtight impregnation vessel, and pressure was then reduced. A liquid chemical called a monomer was introduced into the vessel, and an overpressure was applied to force it into the interior of the wood, filling the voids and cells. The irradiation step came next, wherein the monomer-soaked wood was hardened or polymerized into a wood-plastic combination. The actual equipment at West Virginia looked like this: loading the wood, the impregnation step, and irradiation, which was accomplished by lowering the containers to the bottom of the pool next to the cobalt-60 radiation source. The final product had all of the aesthetic appeal of wood, but many of the properties were improved. For instance, it could be sawed or planed or drilled or turned with conventional tools. Indeed, it was wood, but wood with its cellular structure filled with plastic to give a unique new material. The Atomic Energy Commission undertook a greatly expanded program to catalog the properties of wood plastic materials. Variables were narrowed to several species of wood, including pine, maple, oak, and fir. Among the monomers used were methyl methacrylate and vinyl acetate. Some of the properties tested included compression tests, impact strength, abrasion tests to determine wearing characteristics, bending strength, and other important wood characteristics. General results showed the following improvements of irradiated wood plastic compared to untreated wood. Hardness, up 300 to 500%. Abrasion resistance, up 200 to 300%. Compression strength, up 100%. Toughness, up 100%. Dimensional resistance to humidity change, up 200 to 300%. But not only were its functional characteristics enhanced, even its aesthetic qualities took on new glamour. The product could retain its natural wood grain and color, or by adding a dye to the plastic with which the wood was impregnated, it could be colored throughout, or dyed to match the stain of any wood. It's difficult to nail wood plastic because of its high plastic content. This, however, can be overcome by pre-drilling or gluing. Conventional equipment gives irradiated wood plastic a hard, beautiful satin-smooth finish, which actually exists throughout the wood. In practical terms, this is what it means. A cigarette burn on wood produces an ugly scar, which normally would necessitate a new finish. But with this hybrid, whose finish extends throughout the entire structure, a piece of sandpaper or steel wool is all that is required. Enough buffing to remove the scar, and underneath it, the same satiny finish. With many properties of irradiated wood fairly well pinpointed, and while others were still being identified, the AEC undertook another phase of the program with the Lockheed, Georgia company, which by this time had begun to undertake its own program of developing and marketing wood plastic products. This effort was aimed towards converting standard wood products furnished by private companies into wood plastic and returning the samples for evaluation by the participants. Most of these samples came to Lockheed, Georgia as blanks, that is, semi-formed units from which the finished products were shaped. These, for instance, are baseball bat blanks. And these are blanks for table legs. Lockheed, Georgia gave the wood the impregnation plus radiation treatment, and then sent the polymerized blanks back to the companies that owned them. They were then finished and tested to the manufacturing company's own standards and specifications. From a list of nearly 200 companies which asked to be included in the evaluation, about 80 were selected for participation. The findings from these laboratory studies seemed clearly enough to open up yet other industrial paths. There were, of course, substantial questions to be answered before the laboratory experiments could be converted into products to be manufactured and sold. And it was AEC's responsibility to generate programs which would provide the answers. Further investigation showed that it might well become possible for a manufacturer to produce the wood plastic composite for about 80 cents a board foot. One of the first questions was there a sizable enough market in which the material at that price could compete? The new product will be most competitive with pre-finished, relatively high unit cost flooring. A market research survey found that a market did indeed exist, one which represented many millions of dollars of market value. For example, the manufacture of wood products that could combine toughness with aesthetic qualities for commercial establishments, such as schools or institutions. and even private homes, where furniture cannot always be protected from a certain degree of punishment. It ranges from these to many other items where the requirements are for appearance, permanence of finish, ease of fabrication, and stain resistance. And it very definitely included flooring, which must stand up under steady, heavy wear. Here, then, is a new material with a host of improved properties, with good working characteristics, with favorable market potential, and one for which economics appear to be realistic. Let's take a look at some of the commercial plans and activities currently going on. The earliest entry into the wood plastic field is the American Nova Wood Corporation of Lynchburg, Virginia. One of its most important applications is institutional or commercial flooring called gamma par, where high wear, low maintenance characteristics are important, such as in this meeting hall. In early 1969, American Nova Wood was awarded a contract to provide over 400,000 square feet of flooring for the new Kansas City International Airport. Over 1.5 miles of guardrails, paneling, and other Nova Wood products are also included. Once installed, sanded and buffed, an occasional damp mopping of Nova Wood is sufficient to maintain its striking appearance, which often enhances the warmth and beauty of natural wood. Other applications of high wear areas are ballroom floors, basketball courts, and bowling alleys. Another large volume use will be in furniture and furniture parts. This table, now several years old, was made by the Stanley Furniture Company from a black dyed birch and methyl methacrylate composite. The top is 1/4-inch thick wood plastic glued to a core stock, and the edges are from solid stock. Another table was made from a maple and methyl methacrylate composite by the Kraler Manufacturing Company. It is solid wood plastic throughout. Certain parts of furniture, such as arms, could provide a colorful and attractive appeal. As could picture frames. Textile spindles are now made routinely. Industrial dies and molds have been fabricated. Here, a wood plastic die is being made for the air cleaner on a carburetor. From it, the final metal mold will be made, and finally, the end product. All in all, the uses for this new material are limited only by the user's imagination and desire to be creative. The basic versatility of wood, now enhanced with new properties, permits an endless array of both large-scale and small-scale uses of wood plastics. Research work, supported by the AEC, has drawn to an orderly close, mainly because of the strong commercialization effort now underway by several private companies. One of the latest private companies in this new field is NUMEC, a subsidiary of Atlantic Richfield Company, which located its radiation facility among the rolling mountains and forests in the heart of Pennsylvania. NUMEC is concentrating on the development and production of a parquet-type flooring called permagrain. Made from a combination of red oak and methyl methacrylate, permagrain is offered in several colors and patterns. This floor, in NUMEC's entrance foyer, has been subjected to constant severe abuse by both employees and visitors to the facility. Yet, despite the everyday wear and tear, the flooring still provides an attractive and impressive example of the durability, lasting beauty, and ease of maintenance of wood plastic. Let's take a look at the early production of permagrain. Untreated wood fillets are loaded into carriers, then placed into a pressure vessel where they are impregnated with monomer. Following impregnation and soaking, the boxes of fillets are then transferred to a larger watertight container for the irradiation step. In this case, the cobalt-60 radiation source is located at the bottom of a deep pool, where the samples will remain until all of the liquid monomer has polymerized into solid plastic. After several hours of radiation exposure, the wood is removed from the irradiator, ready for transfer to the automated machinery that forms the flooring. Only the radiation energy has been used to cause this chemical reaction, and there is no trace of radioactivity in the permagrain. This peaceful application of atomic energy has attracted still another company into the wood plastic parquet flooring field. Radiation Machinery Corporation, located in New Jersey, is constructing a very large complex for flooring, which is scheduled for completion in early 1969. More than 3 million curies of cobalt-60 will make up the radiation source, which, when fully loaded, will be the largest source of radiation ever amassed for any commercial application. As with other irradiators, modern radiation engineering technology will assure complete safety to the process, the product, and to those associated with its production and use. This is an artist's rendering of the completed facility. Complete automation of a large plant is quite feasible, as an engineering study by the Vitro Engineering Company showed. The operation would work like this. First, the wood planks are stacked aboard a carrier, which is then transferred to the impregnator for the addition of monomer. Air is evacuated from the wood pores by a vacuum pump down to approximately 1 millimeter of mercury. Pressurization with nitrogen is started, and the pressure is raised to a predetermined level. The monomer is introduced into the carrier containing the wood. Vitro's plan envisions the use of methyl methacrylate. Excess monomer is then removed while still under nitrogen pressure. The impregnator tank is now brought back to normal pressure. The head on the product carrier is then sealed by water flooding, thus maintaining a blanket of nitrogen over the material. Drain water and excess nitrogen are removed. The product carrier is uncoupled from the monomer and nitrogen feed lines and removed from the impregnator tank. It is then placed at the loading station, adjacent to the irradiation cell, and carried by automatic conveyor through 2 sets of doors, which provide a gas lock between the impregnation area and the irradiation zone. The radiation source is radioactive cobalt-60. The product carrier, passing through the first leg of the cruciform-shaped source, is given a high dose rate to get the monomer through the initiation or gel stage. The carrier is passed on each side of the source so that the radiation dose is as uniform as possible. In normal plant operation, many product carriers would be moving through the various radiation tunnels at the same time, as though they were on an endless belt. Finished product carriers move out of the airlock, through the checkout room, and then are unloaded in the finished wood storage area prior to shipment. This plant would produce 24 million pounds of wood plastic composite a year, approximately 5 million board feet. It is clear that wood plastics are even now competitively priced for a number of products and applications, as evidenced by the growing industrial interests in its production and use. Not only can woods be made extremely hard and durable, but also more resistant to insects, weather, and decay. This may provide great advantages in construction in tropical countries, where such properties are important. The accomplishments so far have produced many satisfactions, but the full potential of wood plastic composites is yet to be developed. Great challenges still lie ahead to perfect a technology for veneers, other materials, as well as solid woods. To find industrial shortcuts for production, to cut production costs. But these are exciting challenges that are felt, truly felt, only when new industries are born.